Hello everyone. In the previous video, we learned about the manipulator's Jacobian, right? We learned that if we have the end-effector velocities, linear and angular, and call it vector zeta, then you can write that vector as a linear combination of the columns of this matrix, and the weights for that linear combination are coming from this vector q dot, which has the joint velocities, correct? So by Jacobian, you can go from vector of joint velocities to the vector of end-effector velocities, right? Now, we worked on some examples last time where I calculated Jacobian and we plugged in some values for q dot and we calculated zeta. Most of the time, the problem is kind of reverse. I need specific velocities for the end effector, and the question is, what joint velocities do I need to have to make such motion of the end effector possible, right? So the question is, if I give you zeta and you have Jacobian, how would you give me back vector q dot? And that depends on the dimension of the Jacobian matrix or the number of joints, because if you remember from last time, the dimension of the q dot in general is n by 1, right? So you have n joints in general, while the end effector velocity is 6 by 1 because you have 3 linear and 3 angular velocities. So J in general is 6 by n. So now if I give you zeta, you might be tempted to say, well, I would invert J, right? Multiply it from left side. So this is my zeta is equal to J times Q dot. And so if I multiply both sides by J inverse, then this guy here is going to be identity matrix, and so J inverse times zeta will give me Q dot. And that is right, as long as you can have a J inverse. And you know, we invert matrices when they are a square, first of all, and second of all, their determinant is not zero, correct? So they are invertible. So the case is this top one here, that if the robot has 6 joints, in other words, your Jacobian is 6 by 6, then yes, it's a square. And if the determinant is not 0, so you can find J inverse, then yes, the solution is obvious. Q dot is equal to what? J inverse times zeta, right? And this is called the inverse velocity problem, because again, I know the end effector velocities, I need to find joint velocities. So this is called the inverse velocity problem. Good. And again, J should not have a determinant of 0. Under what condition it doesn't have determinant of 0? That's the topic of the next video. That's where it is not at the singularity locations, okay? We'll talk about it in the next video, that singularities are locations where this J is losing rank, and so the determinant of that, if it's a square matrix, is going to be 0. Because again, determinant is also defined for square matrices. Okay, so if the matrix is not a square, we use something else we call rank, right? So determinant, inverse, and some of these linear algebra tools that we have, they are mostly defined for square matrices. But for rectangular, there are some other tools that we're going to see. For example, instead of determinant, we use rank. Instead of, let's say, eigenvalues that we have for square matrices, we have singular values. And instead of inverse, you're going to see in the third case, we use something called pseudo-inverse. So we still can deal with basically rectangular matrices for J. Good, so that's the first case. And let's look at an example. For example, here, if we go to the 2DOF robot, right? And let's say we have this A1, and let's say this A1 here is, let's say 100 mil. And then you have this A2 to be, let's say 80 mil. And then you have two angles here, theta 1 and theta 2, where theta 1 is like, for example, 30 degrees, and theta 2 is, for example, 45 degrees. And at this point, I want my end effector to move with such velocity. So if I give you zeta here, this zeta is basically, now here it depends on how you define zeta. If you define zeta as a 6 by 1, your Jacobian for this 2 degree of freedom robot is not going to be square, right? Because if you define this as 6 by 1 and this robot, the q dot of it is only 2 by 1, correct? Then your j has to be what? A 6 by 2. So n is less than 6, and that's a separate story, okay? And we're gonna talk about it when n is less than 6. That's the second case. So here, to achieve this goal, we neglect the three angles and the z component, okay? So we modify this zeta. This zeta is not gonna be the same zeta that we talk about here. We modify it, we neglect all of the out of plane motions. So we make this a 2 by 1, so we can also take a look at this and make it a 2 by 2. Okay, so here again we modify zeta. And so all here I care about are the x and y velocities. So what I want here, my zeta to be only v of the end effector, and basically it's only x dot and y dot of the end effector in base. And let's say the numbers I want is some big number y. Let's say, for example, 120 millimeters per second y, and then let's say negative 20 millimeters x, right? Because you clearly see it is opposite to the direction of x. Good, so that's x and y. And now here, this is gonna be 120 and negative 20. My J matrix, if you remember the general format of it, my Q dot is, by the way, theta 1 dot and theta 2 dot. My J matrix, if you remember, this one was negative A1 sine 1, and then negative A2 sine 1, 2. This one negative A2 sine 1, 2. This was A1 cosine 1 plus A2 cosine 1, 2, and then A2 cosine 1, 2. So again, here I'm just trimming the J matrix. So now all I need is to plug in the numbers here, right? Just plug in these numbers using those angles and the length of the members, get this J, and evaluate. And here we go. Let's do it with MATLAB. So we say zeta is equal to 120 and negative, or negative 20 and 120, right? Because here your y is bigger, so actually here I have to change the order. Negative 20 and 120. And so let's go back and calculate it. That's your zeta. Then you have J to be A1, where A1 was, so we have 180. So 100 times, or negative 100, right? It was negative A1 sine of theta 1, and negative A2 times sine of theta 1 plus theta 2, correct? And then the next component is simply just this. And then you had this guy, but with cosine. Right? And then you only had this one for element 2, 2. So that's your J, and now we say what? We say inverse of J times zeta, and this is my vector Q dot. And it says yes, you have to turn your Q's at the rate of 1.566 radians per second and negative 2.32. Okay, so if we solve here, theta 1 dot is 1.5, let's round it, 1.57, negative 232. So positive means counterclockwise, negative means clockwise. So this joint has to go joint 1, as you can see, right? Again, it's positive means counterclockwise. This is negative means clockwise. So for this joint, I rotate it like this. For that joint, I rotate it like that. Okay, and that gives me the motion that I want. And you might say, well, this joint is rotating clockwise. How can the end effector goes like that? Well, that is mostly coming from this first member. Okay, so that is the solution here. And that is called the inverse velocity problem. How fast should I rotate each one of the motors at the joints to achieve that end effector velocity? And you can check back, right? That's your J. Now if you multiply your J by Q dot, see if you get the same numbers back, and you see you do. Okay, so you see I can achieve that negative 20 and plus 120. Okay, so this is when, as I said, the joints are, the number of joints is equal to the number of basically velocities that you desire from end effector. So here I expected only 2 velocities from the end effector, and I had 2 joints, so it was okay. But in general, as I said, when you consider everything 3D, your joint really has 6 velocities, and so it is only possible to solve the problem when you have 6 joints. So here we kind of change the nature of the problem to make it solvable. Now the question is, what happens when you have less than 6 joints? So basically that is going to be the exact same problem that we solved, except that we go and consider this robot completely what? Completely 3D. If that is the case, then my J here is not going to be just that, correct? My J is going to be what? So let me clean this up, and let's look at the J together and see if we can achieve anything. So J in general, if you remember, for this robot, it has 0, 0, 0, 1, and then 0, 0, 0, 1. Okay, so that is what you have for this robot, times Q1 dot and Q2 dot, and then you have to get a zeta which has 6 elements in it. Correct? So now what? Now what numbers can I enter here so I have a solution? So let's say I still keep that -20 and 120, but all I need here is to just add a number other than 0 for z dots. So just any number, just 1, okay, or 2 or 3, any number other than 0, I enter here, let's say -2, and do the rest as 0, and then here we have to think about it. But even just one of these, any one of these three numbers that I did in green, any number of them, is other than 0, it's impossible to achieve that. Why? Because when I multiply this row by theta 1 dot and theta 2 dot, this element will be 0 automatically. And the same thing for here and here. So anything that I put here into these three numbers has to be 0. I can never expect a robot that is planar to achieve a motion out of the plane. It's impossible. And that is what we are talking about here in the second criterion. That the rank of J and the rank of J and zeta has to be the same. Another way that people describe it is they say zeta has to be in the what we call if you know linear algebra, when that is the case, we say it is in the range space. Okay, so we call it is in the range space of J. So in general, in linear algebra, we define two ranges for, or two spaces for a matrix like J. One of them is called range space, the other one is called null space. Okay, so null space are the space formed by the vectors that when I multiply J by those vectors, I get vector 0. Okay, the space formed by all of these vectors x, we call it what? We call it the null space. Okay, now range space means when I multiply J by those x vectors, I'm not going to get a 0. It's not going to be what? Equal to 0, but some elements of it could be 0, like in this case. So when I multiply J by x, it's not going to be all 0, but it is going to be of form, some number, whatever you want to call it, some other number, and then 3 zeros, and then another number. Okay, so anything that is in the range space of J will definitely have elements 3, 4, and 5 equal to 0. And if this zeta is not in that space, which basically means the form of zeta is different from this, which means any of these elements are non-zero, that means there is no solution. So in general, when the number of joints is less than 6, in general, there is no solution. Unless your zeta follows the format of the output of Jx, which we call it in the range space of J, or another way to check that is the rank of J and the rank of J concatenate to it, zeta, is the same. So what does that mean? So that is my J, correct? And it has a rank. What is rank? As you know from linear algebra, rank is the number of independent columns, linearly independent columns. So here, let's say this column and this column are linearly independent. When is it that they are linearly independent? Again, it goes back to the notion of singularity. If the robot is not in a singular position, then the two columns are linearly independent. Okay, so let's assume it's not in singularity position right now. And so these two columns are linearly independent, fine. Now, if I add zeta to J, what does it mean? It means I have the very exact same thing Okay. But I also have the elements of zeta. So let's say here that negative to any, 1 to any, 0, 0, 0, and this number that we are going to discuss. So as you can see, the rank of this matrix has to be the same as rank of this matrix. And when can that be? When this zeta vector is following the format of these two other columns. When the format of that is like the other ones, so two non-zero values, three zeros, and again a non-zero value, then the ranks are the same. Otherwise, if one of these numbers is, let's say, non-zero, so let's say it is 10, then this can be another linearly independent column added to those. So rank of this can be 2, rank of this can be 3. So when adding zeta to j is adding to the, by adding zeta to j and concatenating like this, the rank of this goes up. That means your zeta is not following the format of columns of j, and that means it's not in the range space, and that means there is no solution. Now, if it follows the format and it is in the range space, can I find a solution? The answer is yes, and you can do it by Gauss elimination method. So in this case, let's say the format of it is like the rest of the columns. Now let's talk about this last number here. How much is this? Can I determine this independently? Well, the matter of fact is not really. Okay, for example, if I say this number is, remember last time my numbers were 1.56 and negative 2.32, right? So if I say what is sum of the elements in Q dot, that's negative 0.7545. And if I choose the last number to be anything different than this, what happens? Well, let's just choose it to be 1, for example. Okay, just for the sake of checking. So that number is definitely different than this. Can I get a solution now? Okay, can I get a solution? We are going to check it right now, if there is such a solution. By the way, what is this last one? What is it? What's the meaning of this? This is what? This is your omega z, correct? This last element here is your omega z. You have no omega y, you have no omega x because everything is in the xy plane, and you have no z dot, of course. But what is omega z? Well, in this case, clearly you see that the angle of the end effector with respect to the horizontal axis, if you call it theta z, your theta z is simply theta 1 plus theta 2. Therefore, when you take time derivative, your omega z is theta 1 dot plus theta 2 dot. So once you determine theta 1 dot and theta 2 dot from setting basically what? The first two rows multiplied by q dot by these numbers, as we did last time, and find the q dot that we did, and again we get these numbers here. The last one is out of your control. The last one is automatically going to be sum of these two numbers. If you set it separately to something else and say, well, I will decide about this myself, that means now you have only two parameters to control, theta 1 and 2, but you want to get three equations satisfied: the x dot equation, the y dot equation, and the omega z equation. Can you do that? The answer is no, you cannot. Okay? Because again, from the first two numbers, I get those two theta 1 and theta 2 dots that I just showed to you, correct? And then this last one, when I multiply these two numbers by theta 1 dot and theta 2 dot, the last number is going to be different than this theta. So if I want to add a 1 here, that is not going to be possible, okay? So you see, finding the solution is very, very hard, because if I just look at these three rows, these two rows and the last row, what do I get? My set of equations will be like this: x dot, y dot, and omega z, all for end effector in base. This is equal to negative a1 sine 1, negative a2 sine 1, 2, negative a2 sine 1, 2, a1 cosine 1 plus a2 cosine 1, 2, and then a2 cosine 1, 2, and then 1 and 1 times q1 dot and q2 dot, or in this case theta 1 dot and theta 2 dot. Okay, you see I have two unknowns and three equations. And you know, in general, when my number of unknowns is less than equations, as long as the equations are all linearly independent from each other, there is no solution. Okay, so adding this last parameter here is not going to allow me to solve for it. I have to exactly know what number comes out of the first two rows and then add some of those numbers here. Otherwise, there is no solution. And since I don't know it ahead of time and I can put any number here, guess what? I'm not going to find the solution. That's why last time we trimmed our J matrix to only this, and we said all we can get out of this robot is x dot and y dot. Forget about omega z, because omega z will automatically be determined by theta 1 dot plus theta 2 dot. It's out of our control to determine that. All our robot can do is x dot and y dot, because it only has 2 degrees of freedom. Okay, so you see, in general, this is not solvable. It's not solvable unless you're just lucky to exactly enter the number that comes from the first two columns, added them together. So in general, the answer is no. There is no solution unless you are so lucky that rank of J and rank of J added to it zeta is the same. And that happens very, very unlikely, that you're so lucky to enter exactly all the numbers for zeta. So in those cases, as I said, you have to either reduce the degrees of freedom, the expectations on zeta, trim the zeta down so that J can go to a square matrix, or you cannot find any solution. Now, sometimes, on the other hand, you have more joints than 6, right? So your Q dot is like 8 joints, and so your J is going to be, for example, like 6 by 8. What does that mean? That means you have more variables than what you expect out of zeta, because all you expect from zeta are 6 numbers. But you have 8 degrees of freedom, 8 Q dots to make it happen. So basically you have more unknowns than equations. And you know, in general, when you have more unknowns than equations, how many solutions exist? If you watch my video that I published on my channel for solution of linear equations, you see I have talked about all of them. Just go to my channel, go to engineering mathematics, and here, this is the last video I published, system of linear, square over and under constraint equations. So I explained all of this. If you have a set of a square system, which is equal unknowns and equations, the first case here, right, that you have 6 joints, then there is a unique solution, provided that the right-hand side is not all zeros and the determinant is not all, also zeroed of the coefficient matrix. If the system is over-constrained, right, which means you have more equations than unknowns. That's the second case. Then there is no solution, and if the system is under constraint, so you have less equations than unknowns, then in general there are infinitely many solutions. Okay, so let me add that for you here. There is no solution in general. And here what? There are infinitely many solutions. Okay, and out of these infinitely many solutions, how would you pick one if you have to? Well, there are different ways to talk about it, but I guess the most common one that we always talk about is the least square solution. Okay, so what we try to do is to reduce some of the square errors in the equations, and that gives us what we call the least square solution. Okay, which is the pseudo inverse of J times zeta. And here pseudo inverse is J transpose times JJ transpose inverse. Okay, so this whole thing here is what we call the pseudo inverse, and we show it with J plus. That times zeta gives us a least squares solution. What is least square solution? Let's talk about that. So if I have more joints, like in this case, let's say what? In this case, I have let's go to 3 degree of freedom robot and talk about that. I'm just trying to go with simpler cases for you so you can see that. Good. So let's say here I have the 3 degree of freedom robot, planar. And so I have 3 angles, theta 1, theta 2, theta 3. And let's say again, all I expect from this end effector is x dot and what? Y dot. I do not expect anything else. So I modify my zeta and I make my zeta again to be some x dot and some y dot for the end effector in base. Okay, again, that's not the actual zeta, it's a modified version of zeta, but this is a 2 by 1. Now, can I get this by multiplying the Jacobian matrix times vector q dot, which in this case your Jacobian is going to be a 3 by 2. And your q dot is going to be theta 1 dot, theta 2 dot, and theta 3 dot. What is the Jacobian here? It is going to be negative a1 sine 1, negative a2 sine 1, 2, negative a3 sine 1, 2, 3. Okay, where a1, a2, and a3 are clearly the length of the members, the angles are theta 1, 2, 3, and the angular velocities are the dots. So here, that's the first element. The next element does not have the 3 in it. It doesn't have the 1 in it. So it is like negative a2s2, negative a3s1, 2, 3. And the last one is simply negative a3s1, 2, 3. And then you have something very similar but with positive cosine. So a1c1 plus a2 c1 2 plus a3 c1 2 3, then simply a2 c2 plus a3 c1 2 3, and then simply a3 c1 2 3. So this is what you have. Okay, so now if I multiply the J matrix by the Q dot and try to satisfy the two equations, you will get two equations and you will get what? You will get three variables. And since the variables are more than really the equations to satisfy, here you have the option to pick one of them just at your own convenience and then solve a 2 by 2 really, correct? Because you really do not need the third variable to satisfy those. And that makes it to be what? Infinitely many solutions, because let's say here, if I determine theta, let's say theta dot 3, and then by myself, and then just whatever I pick, and then theta 1 and 2, I calculate through the equations. So since I can choose any number for theta dot 3, of course, it means infinitely many solutions. Now, how do I pick a solution with the least squares method, which you can see a solution here, pseudo inverse times zeta. So this is what I do. Well, so what we do in this case, we define a cost function, and the cost function is basically to be the norm of the solution. So the cost function we define f is f of theta 1 dot and theta 2 dot and theta 3 dots, the solution. It is going to be the norm of the solution squared, which is going to be theta 1 dot squared plus theta 2 dot squared plus theta 3 dot squared. Or if you call that whole thing vector q dot, you can say f of q dot is simply norm, Euclidean norm of q dot squared. Okay, or if you write q dot as a column vector, you can say it is q dot transpose times q dot. That's another way to write it, correct? Good. So we need to minimize this function, but we have a constraint, and the constraint is j times q dot is equal to what? Zeta. So we have to minimize this cost function subjected to the fact that j times q dot is equal to zeta. So here is a constraint optimization problem, and you know to do that, you form a new cost function e of q dot using Lagrangian multipliers, which is going to be q dot transpose times q dot, and then plus lambda times the constraint equation, which if you bring this jq dot to the other side and set it equal to 0, it is going to be zeta minus jq dot, correct? Because again, you can write this like that. And so the goal is to keep this constraint valid as much as possible, keep it close to 0, and minimize this function. So we combine them using Lagrangian multipliers. And if you know how to basically solve an optimization problem with Lagrangian multipliers, so we take the partial of E with respect to Q dot, and we also take partial of E with respect to lambda. Set them equal to 0, and if you do these and go through solution, I leave a little bit of that for you to practice, then you will see that the optimum solution, Q dot star if you want to call it, is going to be j pseudo inverse times zeta, where this j pseudo inverse is j transpose times j transpose inverse. And why do we call it pseudo inverse? Again, I mentioned in some of my videos, but if you multiply this j pseudo inverse by j, what's the result? Well, let's do that. you have to multiply it from the left, not from the right. This guy is called the right pseudo-inverse. So you multiply that from the right side by j, and if you see here, you have this entity, which is a square matrix, and then the inverse of that square matrix, and multiplying two things that are inverse of each other, and they are both a square, will give you what? Identity matrix. So you see, when I multiply that matrix from the right-hand side to j, the result is going to be I. Okay? So just keep in mind that if my system is underdetermined, like this case, and I have more unknowns than equations, then I have infinitely many solutions. One of the many solutions that can minimize the norm of the solution is this guy here, j pseudo inverse times zeta. And you might say, why should I minimize the norm of the q dots? Well, that's to save energy, right? Because you can have a solution where the value of q dots, the entries of q dot, which is theta 1 dot, 2 dot, and 3 dot, they can be very large. So I am going to achieve the same speed for the end effector, but instead of, let's say, rotating this at 1 RPM, 5 RPM, and 10 RPM, I'm going to achieve it with 50 RPM, 60 RPM, and let's say 30 RPM, right? And the faster you have to rotate the links of the robot, the more energy you are going to waste. So what you are really doing by forming this norm and trying to minimize it, while at the same time achieving your goal of end effector velocity, you are trying to minimize the energy spent to achieve such zeta. Okay, so that's called the least square solution. So hopefully I could tell you about this important problem of inverse velocity and different scenarios that can arise depending on the dimensions of j, or the number of joints, right? Which there is no solution. There are infinitely many solutions. We pick the one that minimizes the energy spent, and when it is square, and you can have a unique solution provided that this matrix is invertible. And we'll learn in the next video that this guy is invertible if and only if the robot is not in the singularity, or this matrix basically has a non-zero determinant. Okay, so we'll talk in the next video about singularities and clarify this topic, and then we move on to the other applications of Jacobian in robotics. Thank you so much.